Welcome to all of my students. So once again I am back, and today I will deliver lecture number 20, and I will start unit number 3. And I am recovering from my illness, so I will start not at full strength, but I will try to explain something. So unit 3, lecture number 20. So this is basically chapter number 2. Unit 1 and Unit 2 comprise of first chapter, and Unit 3 is of chapter 2, excluding one topic. So in this we will discuss green equivalences. Green is a mathematician and who describes some relations, and those relations are equivalences, and which are of very importance in semigroup theory. And so your topic is Green's equivalences. So let S be a semigroup. So we define equivalence relations on semigroup S as follows. ALB. Green sequences are, this is L, R, H, D, G. So these are 5 green equivalences relations: L, R, H, D, G. So we define ALB is like this: S1A is equal to S1B. In this way it is defined. Here A comma B belongs to S, of course. So we say that A and B are related to each other when S1A is equal to S1B, correct? And it implies and re-implies there exist X comma Y belonging to S1 such that XA is equal to B and YB is equal to A. Similarly, we can define ARB implies AS1 is equal to BS1, or implies re-implies there exist XY belonging to S1 such that AX is equal to B and BY is equal to A. So in this way L and R are defined, and we can check that these are equivalences. One can check very easy that they are reflexive, they are symmetric, and they are transitive relations, correct? What is S1A? This is the S1A, as I told in unit 1, S1A is the smallest ideal of S containing element A. S1A is the smallest left ideal of A containing element A. This is a fact. So verify this. Verify by yourself that S1A is the smallest left ideal of S. S1A is the left ideal of S, and not only left ideal of S containing A. It has 3 parts basically. S1A contains A, S1A is left ideal of S, and it is the smallest left ideal of S, isn't it? In a similar way, it's the dual part, that is AS1 is AS1, if you talk about AS1, then AS1 is the smallest right ideal of S containing A. So these things all of you can verify by yourself how it is so. So A and B are related to each other when we say that the left ideal. So S1, when S1A is equal to S1B, then we say that A and B are related to each other. Now I define a relation, another green equivalence relation, that is H. H is what? L intersection R. And D is defined as L join R. And AJB is defined as S1A S1 is equal to S1B S1, implies re-implies there exists X, Y, X dash, Y dash belonging to S1 such that X A Y is equal to B and X dash B dash X dash B Y dash is equal to A. So AJB is defined as S1A S1 is equal to S1B S1, and it is equivalently you can say like this, isn't it? And so in this way, these five Green's relations are these are the five equivalences on a semigroup S: L, R, H, T, J, and it plays a very important role in semigroup theory. So now, if we think about what is the relation in between these, so we will see that what is the relation between L and H, what is the relation between L and D, what is the relation between L and J. We can also see all these things. Before this, there is a fact that L is a right congruence on a semigroup S, and its dual part is R is a left congruence on a semigroup S. So this is a very trivial proof. I will do for L and left as an assignment for R. So see, we have to prove L is a right congruence. See, we know that L is the equivalence relation, isn't it? All these are equivalence relation on a semigroup S, correct? And all are what? Basically, we see that L S cross S and R S cross S and H S cross S, D S cross S, and J S cross S. These are what? These all are equivalences on a semigroup S. So being equivalences means that they are relation on a semigroup S. So of course they are a subset of S cross S, correct? And we see that H being L intersection H is what? L intersection R. So of course H is contained in L, and also it is contained in R. And also we see that L is contained in D also, and R is contained in D also, and D is contained in, because what is D? D is defined as L join R. L join R. So of course L is contained in L join R, and R is contained in L join R. and also D is contained in J. Now, how it is? I will explain it. Okay, how D is contained in J. Before this, I have to do some more facts. So anyway, first I will prove that L is the right congruence on semigroup S. So to prove L is the right congruence on a semigroup S, what I have to do? See, we know that L is equivalence relation on a semigroup S. So to prove L is the right congruence, we have to prove L is the right compatible. Right compatible. So to prove right compatible, what we do for any basically, what is our claim? For any C belongs to S and A comma B belongs to L, we have to show AC comma BC belongs to L. Basically, we have to show this, correct? So ALB implies what? S1A is equal to S1B, isn't it? Or you can say it implies there exists XY belonging to S1 such that XA is equal to B and YB is equal to A, correct? Now XA is equal to B, so it implies that XAC is equal to BC and YBC is equal to AC, correct? So we can also write, it implies that XAC is equal to BC. We can apply this associativity, and YBC is equal to AC. So see, if you see the definition of ALB, if you see the definition of relation L, how relation L is defined, so we see that XY belongs to S1 and X into AC is equal to BC and Y into BC is equal to AC. So what does it imply? It implies that ACLBC. So it implies that L is right compatible. So being right compatible, equivalence relation is what? Right congruence. So you can write hence L is right congruence. Correct. Now I left R as the left congruence on semigroup S. Now this was basically proposition 2.12 which I have proved. Now I will do proposition 2.13. Proposition 2.13. The relations L and R commute. That is LOR is equal to R. L composition R is equal to R composition. We have to prove this, correct? So let's prove. Let S be a semigroup. and A comma B belongs to S such that A B belongs to L. A comma B belongs to L composition R. That has to be a semigroup, and take any A comma B belongs to L composition R, where A B belongs to S, of course. So basically we have to prove that we have taken an element in L composition R, isn't it? And now we have to prove that A comma B goes in R composition L. Then L composition R will be the subset of R composition L. And conversely, we can prove that R composition L is a subset of L composition R. So you see, A comma B belongs to L composition R. It implies what? There exists C belongs to S such that A comma C belongs to L and C comma B belongs to R. Correct? Now A comma C belongs to L. It implies what? There exists X comma Y belonging to S1 such that X is equal to C and YC is equal to A, and C comma B belongs to R implies there exists UV belongs to S1 such that CU is equal to B and BV is equal to C. So these things we have, correct? So basically, see, what is the idea? Basically what we have to prove? We have to prove that this AB goes in R composition L. So when this AB will go in R composition L, this AB, when it will go in R composition L, it can only go in R composition L if this condition rises like this, that is A comma D belongs to R and D comma B belongs to L. Correct? Implies it implies. So this AB will go in R composition L only when we find out such element D such that A comma D goes in R and D comma B goes in L. So if we are able to find such element D, then we are done. So we are in the search of such element D. Now let's choose. Right, D is equal to YCU. Of course, YCU is a member of S because Y and U and C, these are elements of the S. So when they operate, it will again go in S. S is a semigroup. So this is an element of D. Now we show that A comma D goes in R and D comma B goes in L. See how. Now AU is equal to what? A is what? YCU. This is what? D. and dv is equal to what? ycuv is equal to what? ybv dv, because d is ycu and cuv is what? cu is what? b. So ybv and bv is what? c, that is yc, and yc is what? yc is what? yc is a. Hence ARD also YB is equal to what? YCU So you see it is ARD. Why? Because when we are multiplying A by on the right side, AU is equal to D we are getting, and DV is equal to A. So it is satisfying the criteria of relation R. So that is why ARD. Now also YB is equal to YCU is equal to D, and XT is equal to XYCU, and this is what? XAU, and this is what? CU, and this is what? B. Correct? And so D from here. So XD is equal to XYCU is equal to XAU is equal to CU is equal to B. Because YCU, what is YC? YC is what? A. YC is A here. So it is XAU. Now XA is what? XA is C. Where it is? Yeah, this is XA is equal to C. Correct? So it is CU, and now CU is what? CU is B. CU is B. So now you see that what is it is satisfying? It is satisfying the criteria of DLB, and so DLB because XD is equal to B and YB is equal to D. So DLB. So in this way, what we have